In today's lesson, we are going to be moving on from one variable analysis to two variable analysis. And we're going to be focusing on linear correlations. So we're going to go through, we're going to look at what what linear correlations can tell us, how we can use it, and then we'll go through an example where we actually have to do one ourselves. So we're going to be looking primarily at scatter plots, and scatter plots are a way to graph independent versus dependent variables to check to see if there's a relationship. So this is the main graph that you should be using when you have two variables, because those are going to be the x and the y, the independent and dependent. All the other graphs that we've kind of talked about, right, the box plots, the bar graphs, histograms, pie charts, those are all one variable graphs, right? We're only looking at one variable. But when we look at scatter plots, we need two. Right? So whether it's the weight in car or the weight of a car versus the city miles per gallon, whether it's your writing score versus reading score, right? We have two variables in our data. Each point represents two values. Right? So each individual, whether it's a student, will have a writing and a reading score attached to their coordinate or their point. Each car is going to have a weight and a mileage or city miles per gallon at each point. So when we're using scatter plots, we want to look for a correlation. And basically, to analyze the relationship between two variables, we create a linear model through a process called linear regression. Now, it sounds fancy, but really we're just going to be getting technology to create a line of best fit. Right, so essentially, when we talk about a linear regression, we're talking about a line of best fit. It's the same thing. Now, correlation, what we're looking for is the extent to which two variables are related to each other. Is there a relationship between two variables, or the two variables that we're looking at? Now, one thing to keep in mind, and we will talk about this in the next lesson, is that just because two things are related to each other does not mean that they cause each other, or that one causes the other. Right? So just because there's a relationship does not mean that one causes the other. We could have two types of correlation, positive and negative. If we have a positive correlation, that means as our x variable increases, the y variable does the same thing. So for example, if shoe size increases, so does your height, right, typically speaking. A negative correlation is that as the x variable increases, the y variable decreases. So this might be something where as TV use increases, reading time decreases, right? The more time you spend on TV, the less time you're going to spend reading. When we're looking for the correlation, we want to be mindful of what the independent and dependent variables are, not just because that's our two variables in our data set or in our scatter plot, but because it does help us understand what we're looking at. Right? So the independent variable, right, is usually always placed on the x-axis, and it's normally the first in the table of values. The independent tends to be the first column in our table of values. Now, the reason we want to know which one is which, because basically the independent is the variable that causes a change in your dependent variable. Right? The independent variable is the one in charge, so to speak. It's what's causing a change in the other variable, or that's what we're seeing. If there is a relationship, basically saying, does the independent variable cause a change in the dependent? Right? So we look at time spent with doctor and outpatient consultant and their satisfaction. So the more time they spend talking to a doctor, the more satisfied they are with their treatment. Right? Looking at the plant growth, the amount of water. So as we increase the amount of water, the plant growth rate increases. However, if we feed it too much water or give it too much water, then the plant growth rate can decrease. Right? So we see that kind of change between the two variables. Now, when we talk about a correlation, when we talk about a relationship, one thing that we can do to help us with that, or to really see if there is a relationship, is draw a line or create a line or an equation of a line, right? Create a line of best fit. So basically, we use a linear regression model, or technology, to create a line of best fit, and it'll be given to us in the form y equals mx plus b. Right, so you might have to go all the way back to grade 9 to remember y equals mx plus b, the equation of a straight line. Y represents the dependent or response variable. X represents the independent or predictor variable, right? What's going to cause the change. M represents the slope. And we talk about the slope as a measure of increase or decrease in the dependent variable, or of the dependent variable, for every 1 unit change in the independent. So every time the independent goes up, then the dependent will either increase or decrease by a certain value, which is the m value. B represents the y-intercept, right? This is basically the value of the dependent variable when the independent is 0. Right? Basically the starting value. When we don't have anything of whatever the independent is, what is the value of our dependent? So we will be looking at not just creating a line of best fit, but creating an equation to represent that line. Because this way, now we can use this equation to make predictions, right? Because it's essentially a model of the relationship, or of a possible relationship between two variables. When looking at the equation of a line, the correlations, there are 2 statistical values that we want to look at. One is the coefficient of determination. So this is, or otherwise, the r squared value. So this is a number from 0 to 1, and it gives the relative strength of the relationship. Right? So basically it's telling us, okay, if there's a relationship, how strong is it? How strong is the relationship between the 2 variables we're looking at? And how we read it is that, say for example, if our r squared is 0.44, that means 40% of the variation of the dependent variable, or the change of the dependent variable, is due to the variation of the independent variable. So in this example, if we had a 40 or 0.44 r squared value, that means that less than half of what's happening to the dependent variable is due to the change that we're making in the independent. Right? So if we look at the TV use and time spent reading, if we graph that relationship, or we graph that data, and we got an R value of 0.44, basically it says 44% of the change or the decrease in reading time is due to the increase in TV time. The rest would be due, the other 56% would be due to randomness, other variables that are coming into play, things like that. So it just gives us a relative strength, tells us how much of the change is actually due to the independent variable. Along with that, we also have a correlation coefficient, our R value. Now this is a number from -1 to 0, and it gives us 2 things. It gives us the strength and the direction of the variables. So how closely it models a linear relationship. How close does our data fit a linear relationship? Not all data forms a linear relationship. It might be quadratic, it might be exponential, things like that. But for our purposes, we're going to be looking at a linear relationship, right? Which is the two outcomes. If one goes up, the other goes up. If one goes up, the other goes down. Those are 2 possible scenarios. It's also a measure of how well the line of best fit fits the data. How well is that line there for making or predicting? Right? How consistent is the data? Does it fit that line? And to calculate it, essentially we calculate it by taking the square root of the r squared value, which we just talked about. There is a range. There are ranges, right? In terms of the strength, right? Direction, relatively straightforward. Positive linear means it's going up. Negative linear means it's going down, right? So like a positive slope and a negative slope. Think of it like that. I have to draw one, just a quick example. Right? Positives going up, negatives going down. And there's 3 kind of categories when looking at the values, right? So because we can have anywhere from -1 to 1, right? 0 is kind of in the middle, basically saying there is no correlation. Right? So if we want to, there's no correlation if we have an R value of 0. Then from anything from 0 to 0.33, positive or negative, right, we consider it weak, to be a weak correlation. From 0.33 or negative 0.33 to 0.67 or negative 0.67, right, anything in between that interval is considered moderate. There's a moderate relationship between the two variables. And then finally, 0.67 to 1 or negative 0.67 to negative 1 means it's a strong relationship. Right, that's essentially saying what points or 0.67. If we converted that or squared that, just to kind of answer the next previous kind of question. Right? So again, that 44. Right? So 0.67, even though it doesn't seem quite that high and doesn't really give us that strong of an R squared value, right? That's only about 45% of the data is affected by the independent. That is our interval to tell us if it's a strong relationship. So we will, a lot of these values that we're talking about, we're not going to have to do any calculations to get them. The technology is going to give it to us. Right? So we just have to understand how to interpret it. So the idea of regression, what is a regression? Right? We talked about how it's a line of best fit. Basically, it's a mathematical function that describes the relationship. So kind of what we had previously mentioned. It looks at a couple things. It looks at the vertical distance between the line of best fit and each data point, called a residual. Right? So when we look at our line of best fit, that's not always going to represent the actual values that we got. Right? But what it does do, or what taking a regression does do, it does look at the distance from each point to that model, to that line of best fit. Right? Ideally, if you remember making a line of best fit, you want the majority of the data to be relatively close to that line. Right? You want it to go through as many points as possible, try to get it as close as possible. Right? That's the goal. And that's what the technology is doing. It's basically going through and saying, okay, which line will give me the least squares fit? Which is basically saying which one will get me as close to the points that I have as possible while still maintaining a straight line. So again, that's more the technology, that's more the background behind it. So what can we do with this linear model? We now know how to come up with one. We know how to analyze the values or the statistics that come with a line of best fit, right? The R squared, the R value, and how it tells us basically about the relationship. So what else can we use our graphical values for, right? Or our linear relationship, that linear regression, that line of best fit? Well, we can use it to interpolate. Interpolate means predict values that lie within the domain and range that we have, right? So basically we're predicting values with inside the data that we have, right? So it's not just, oh, there's nothing, we don't have anything in these ranges, that's fine. Right? So interpolation is predicting values that lie within our data. Right? So basically anything, anywhere in between the first data point and the last data point, if that's where we're making our predictions, it's called interpolation. Right? Extrapolation is predicting values that lie outside the domain or range. So this is outside the data that we've collected. We're not talking about, oh, it's not an actual value that we collected. We're talking about, is it outside the maximum and minimum value of our data? And then one thing that does come up, right, we usually, when we talk about extrapolation, usually comes with this, with a disclaimer, if the model continues this way, right, and then what we think our prediction will be. And the reason being, extrapolation, we don't know what's going to happen, right? If you were to measure someone's height over the first, say, 15 years of their life, and you were to graph it, right, and ideally, you should have kind of somewhat of a good relationship, right? The idea that as your age increases, your height increases. So we'd have a fairly relative or a fairly decent line of best fit that would draw that. But what if we wanted to use that line to predict for, say, when you're 50, right? You're not going to draw out 40 more spaces or however many spaces you need based on how old you are, right? You wouldn't do that, right? It's just going to take too long. And the other reason being is the model going to continue that way? Are you always going to gain height as you grow older? Right? How many elderly giants do we see walking around? Not that many, right? If you think of an older person, right, your grandparents, family, friends, guardians, things like that, right? If you think of someone relatively older, are they typically tall or short? Right? In my personal case, both my grandparents were small, right? They were smaller. I was definitely larger than them, but they didn't keep on growing, so the model didn't continue that way. Right, so that's why we kind of have that disclaimer. We don't know what's going to happen. We don't know if the model is going to continue. Right? Maybe there's a threshold. Maybe there's a peak that kind of causes it to level out. Right? So that's why we kind of have that disclaimer, because the model might not continue that way. It might drop or rise right after our last value. We don't know. And finally, looking at a residual plot, kind of an option when we look at scatter plots and lines of best fit. So a residual plot is basically just showing us the actual distance. It shows the distance, positive or negative, that each point lies from the line. Right, so it just shows us how far each point is from the line. And it's a little bit easier to visualize, right, because we have this straight line here. The other one, it is a diagonal line. Not that it's bad, it's a good line of best fit. It's the best one that the technology would create, but it might be a little bit hard to see how close or how far some of these values actually are. Right? So if we're looking at that, we can kind of highlight some values, like specifically here. Right? This is an outlier. Right? We can just almost tell just by looking at it. Right, so the reason we have our residual plots is that we can use it. We can use it to look for outliers, right, look for values that don't really fit in, so that maybe we can remove them from the data and recalculate. So let's go through one example. Right, we're going to create a scatter plot for the table below, which shows the distance from home for a cyclist. So what we're going to do, I'm going to kind of pull up a dual screen here. I've already opened up a Google Sheet spreadsheet. Now, if you choose to do this on Excel, steps are a little bit different, but generally the same idea. So I'm going to create my table. We have our time in minutes. And then we have our distance in kilometers. So I'm just going to basically copy over that data. Copy over the data. You can kind of hopefully see it here. So we have 10, 20, 30, 40, 50 minutes. And our distance is 8.9, 9.1, or 8.9, or sorry, 9.8, 8.1, 5.8, 4.2, and 2.3. So I have my data here. I'm going to highlight my data. I'm going to click Insert and Chart. Now in this case, it created a line graph. I don't want a line graph, so it already opened up my chart editor over here. If for some reason that disappears, like so, you can always click on the three dots, go Edit Chart, and it comes back up. So we're going to change our chart type. We want a scatter chart. We can see it here. If we need to, we can scroll down as well to scatter chart. Kind of can't really see it clearly. And we're going to have our scatter plot. So we've created our scatter plot. Now what we want to do, we want to determine, identify the independent and dependent variables. Well, in this case, our independent is going to be the first column in our table. So our independent, our dependent. And if you think about it, the distance from home depends on the time. Right? When we change the time, our distance is going to change. Right? So sometimes these can be a little bit confusing because you could maybe think about, well, if I change my distance, does the time change? And you might say, well, yeah, it does. If I change my distance to something small, then my time should probably increase. Right? You might be able to argue that, but again, are we actually changing the time? Right? And the answer is no. You can't change time. Time doesn't get changed. Right? Time doesn't slow down or speed up depending on anything. So generally speaking, in this case, time is our independent. And the distance is our dependent. Does there appear to be a relationship? If so, describe it. Well, let me pull it back up. Here we can see, we close this. We can see, bring it back out. Right, we can see our graph. Is there a relationship? If so, describe it. Does it look like there's a relationship between our data points? And I would say yes, there does look to be a relationship. Yes. And the relationship is as time increases, the distance decreases. So we do see a relationship. It does look like there's kind of a trend or a pattern in the data. And from what it appears is that as the time increases or as our independent variable changes or grows, the distance from home decreases. We get closer to home, which makes sense. So the next thing we want to do now is we want to determine the equation of the line of best fit and explain what it means. So what we're going to do in this case, I'm going to bring up Excel. Right, so this is just Excel Online. Every student has access to it. Right, you can go to your My Apps and it should say Office 365. You just log in with your student account and you should be able to access the Excel workbook online. You can also download it as well, but the online version works just as well. So I've already entered the data in. I'm going to click Insert up top, and you could go down to recommended charts, or you could go into this Dropbox menu and go down to scatter plot again. You might not be able to see it, kind of hidden behind. Let's bring it. Right, you can see it there now. So I click on it, and now I have my scatter plot, very similar to the previous one where we had it here. Right, so I'll probably just switch back and forth between the two just so we get a good idea of how to use both. I do like Excel a little bit better. It is a little bit of a more powerful program. So we want to come up with the equation for the line of best fit. So I'm going to click on my data point, or my data, and I'm going to select it, and I want to format it. Right, or I could have also right-click format. So if we click format, we want to go down to series. And from there, what we're going to go do is go down. We could check this box to label our data if we really want to. Right, close the drop-down box. But the main thing I'm after is this trend line. So I'm going to click the trend line. And we see that we have our line. I can go down. I can set up a few things. Right. The other main thing that I want to look at is display the equation on the chart. So just a checkbox. So I've displayed the equation. You can see it here. Probably move it around maybe a little bit. Or maybe not. Go back. And I want this to display the r squared value. So another checkbox. So we click that and we get both here. Right, So I have now my equation, y equals negative 0.189 plus 11.71, and the r squared value of 0.9975. So that's how I got those two values using Excel. If we go to Google Sheets, it's the same idea. I'm going to click on the three dots to edit the chart. I'm going to go Customize, click on Series, scroll down to Trend Line, so very similar. We do see that we get our line of best fit now as well. I'm going to scroll down, click on Label, Use Equation. So now I see the equation up here, same equation as I got in the last one, and show r squared value, the other box, and I see 0.997. So very similar, right? A little bit of an extra value here, a few extra values in the equation, but generally the same thing. So either which one you choose is fine. The Excel one tends to be a little bit more powerful, and it can do box plots, whereas Excel or the Google Sheets does not do box plots, at least in a nice way. So we come back to our question. Determine the equation of a line. So might as well bring it up here. So we can see the equation of our line. We've determined that by checking off the box, getting the computer to do it. Negative 0.189 x, where that little star means multiply, so multiply by x, plus 11.7. Now what does this mean? What does this mean? Well, if I look at the m value, the slope, right, the negative 0.189, right, that's our m value. So that's telling us that for every change of 1 in the independent variable, the dependent variable is going to change by this amount. Right? So for every minute, or for every 1 minute, the cyclist gets 0.189 minutes closer to home. Oops. Probably you can see everything. So that is what the m value is telling us. For every 1 minute, the cyclist gets 0.89 meters closer to home. Right, that distance from home is starting to decrease. The other variable, or the other value, is 11.7. That's our b value. And the b value, if we remember back to grade 9, is the starting or initial value. So this 11.7 kilometers, right, the y-intercept means that x is 0 and y is 11.7, right, x and y. So starting initial value, this means that the y-intercept is 11.7. Kilometers. So the y-intercept is 11.7 kilometers. What does that mean? How does that help us? Right, so we can say it's our starting value or initial value. So we could say starts 11.7 kilometers from home. That's the main thing this equation, or that part of the equation is telling us. Right, starts 11.7 kilometers away from home. That's that y-intercept. Determine the strength of the relationship. So again, that's coming back from the r value. So you can see an r value of 0.997, or technically an r squared. Same thing in the other one, we get an r squared value of 0.9975. So the r squared is 0.997 or 75. That third hundred or thousandths of a decimal place doesn't really help. So to find the r value, right, I need to square root both sides to get r by itself. So So my R value for this graph is the square root of 0.997. We get even stronger, 0.998. So therefore, because that value is very close to 1, therefore it is a strong linear model. It's a strong model. We should be able to make strong predictions or very good predictions because the R value is close to 1. So what we can do now is we can start making predictions. We have our equation, right? We have our graph. So if we really wanted to, I could look at this graph here. Right? If I want to predict after 12 minutes, I can go over to where 12 kind of appears to be, and I can go right up to my line and say, okay, this is about, maybe it's about 9, right? Maybe my distance from home will be 9. Sounds a little bit unsure, and it is, because we're just kind of looking. But what we can do is we can use the equation. So y equals negative 0.189x plus 11.7. So this value here, that's our x value, right? That's our independent variable. So we have negative 0.189 times 12 plus 11.7. So basically, we're using the equation to help us solve. Negative 0.08 times 12 plus 11.7. So this means then that after 12 minutes, we will have 11.47 kilometers remaining. Right, so we got done just under 0.27 kilometers, so not even a full kilometer. Predict how far from home the cyclist is after 50 minutes and 20 seconds. Right, so 50 minutes, relatively straightforward. 20 seconds, that would be our 20 divided by 60, or 0.67. Right, so that's how many minutes we're trying to predict for. And so again, we can go and take a look at our graph. We can see that if we're looking for 50 and just beyond, right, this is an example of that extrapolation, right? We're predicting outside this data, so our last value is at 50. Even though we're fractions over, it's still technically an extrapolation, because we don't know. Maybe the distance just drops off. Maybe he doesn't even continue his race or wherever he's at, right? So there is no other data. Otherwise, though, because we can't really see it, we do have our equation that we can always use when making predictions. Now, in some cases, depending on what the number is, it might not be the easiest value or thing to collect. But if you have lots of time, then sometimes it's useful. Negative 0.189 times 50.67 plus 11.7. So after 50 minutes, we'd be down to roughly 212 kilometers. Right, so that would be how many kilometers from home we are. G, when does the cyclist arrive at home? Right, so because we're arriving at home, this is telling us that x equals 0. Or sorry, not x equals 0, when y equals 0. So in our equation, 0 equals negative 0.198 x, because we don't know how many or how long, plus 11.7. Rearrange, we have 11.7 equals negative 0.189x. End up dividing both sides by negative 0.0.189. That should have been a negative when we brought over. 11.7 divided by 0.198, and we get 61.90 equals x. So that means in order for the cyclist to arrive home, they have to ride for 61.9 minutes. How far from home was the cyclist when they started? Right, so when we're looking when they started, we're looking for our y-intercept. So in this case, our y-intercept was the last value, so this was the 11.7. So that means that therefore they were 11.7 kilometers from home. Right, that's how far they were. Ooh. Sorry for that mistake, seeing that not any of these are being brought up. So hopefully you got the last couple ones to hear me talk. We have our y-intercept, or when they started, and the last question for this example, time when they are 7 kilometers from home. So this is telling me my y value. So that means 7 equals negative 0.189 x plus 11.7. Very similar to what we did in question G. So we minus the 11.7. Negative 4.7 equals negative 0.189x. And we get that an x value of 24.87. So that means after it would take them 24 minutes or 24.87 minutes to travel or to make it 7 kilometers from home. So that's all the predictions that we could do using the scatter plot, identifying the strength of the relationship, things like that. Last thing we want to do is just quickly match the following graphs with the appropriate correlations. Right? So which correlation coefficient matches each graph? Some easy ones, right? That's a relatively easy one. An R value of -1. Negative because it's going downwards, think a negative slope. And 1 because that is a perfectly straight line that's showing a decrease. The other next one might be then this one, the mass of ham versus the cost. Right, a positive relationship, it seems the data lines up in a perfectly straight line, so that means R equals 1. Now if we look through, try to find other relationships. R equals 1. Right, we can look at the R values. We could look for, okay, what are the higher R values? Right, and then we can attach it to graphs or scatter plots that look very similar to straight lines. So the only other high value right now is negative 0.96. This does two things. It tells me that my line should be going down, and it should be very close to a line. Well, looking at the other options, the only one left is this one. Right, so R equals negative 0.96. Right, showing that as practice time increases, the number of typing errors decreases. So negative correlation doesn't always need to be a negative thing. If we look at the next R value, 0.29, so again it's positive, not very good though, so that means the data is mostly spread out. Right? I would argue, maybe get something a little bit better. I would argue the shoe size versus math score, that shows a very weak correlation. Right? There's not too much of a relationship between shoe size and math scores. So that leaves us with 0.03 and 0.6. Right, the 0.03, I'm going to bring this up on this side. Right, again, the spot that looks least like a line. Sometimes if it helps, draw a line or try to draw a shape all the way outside all of your data points, right? If you get something, or the more and more squarish, rectangularish, if that's a word, it looks, then that means that the weaker the strength. And the last one, then, that means it leaves us 0.06, temperature versus bottled water sales, right? So let's say there's a moderate relationship between that. As the temperature increases, so does the bottled water sales. I missed writing all these down. 0.03 and R equals 0.6. So the main thing from this lesson is looking at the different types of correlations, or sorry, not the different types of correlations, how to find a correlation, how to find a line of best fit, how we can use it to analyze two variables to see if there's kind of a correlation between them, as well as make predictions, right? Whether it's inside the data predictions or outside the data predictions. And it allows us also to determine whether that line or that line of best fit is a good fit for this data. Maybe it's something else. Maybe it's not a linear relationship, which can happen. Right? Maybe it's something else. The R value will tell us that. So again, when we're dealing with two variables, which you will be at some point trying to find relationships, this is a very important lesson because it goes over all of the different kind of aspects that you'll need when looking at linear